Hey everyone, this is the probability video for today. We're working on conditional probabilities today, so it's going to be a little bit more complicated, but we'll still kind of get through it and it makes sense what it is. So a conditional probability is a probability that something is going to happen given that something else has already happened. So we kind of look at the two questions we have to think about because it is important what we're looking to do. It's like we're looking for two questions to consider. What is the probability of a Carver High School freshman is over 6 feet tall? And then what is the probability a Carver High School student is a freshman and is over 6 feet tall? We're asking really two different questions. When you kind of look at it, the first question is asking, we're looking at two different sample groups. The first question is asking just about Carver High School freshmen. Like if we selected a Carver High School freshman, what's the chance that person's over 6 feet tall? Whereas the second question is looking at the whole school, and now we're trying to pick a student out of the whole school, and if we pick that student, what's the probability that that student is a freshman and is over 6 feet tall? So it's two different things we're looking at, and that's what the conditional probability is the first one. Given that we're looking at the freshman, what's the chance they're over 6 feet tall? So that's what they mean by given something else has happened. So let's go back to our example on the census data. The question we're looking for is what is the probability a college-educated person is married? So what we're looking at there is we're just looking at the college-educated people. We're not looking at everybody else. It's like what's the probability that college-educated person is married? So what you're looking at is you're just kind of looking at that row and then you're trying to find who's married. The probability of a person is a college educated and married. Now we're looking at the whole group of people. And we're looking at both the number of people that have a college education and the number of people that are married, where then we kind of have to back out the people that are both. So we kind of did that yesterday when we looked at it. So it's definitely a little tricky when you're looking at the census data to make sure you get the right, the data tables, to make sure you're looking at the right line in something like this. We'll do a couple more examples as we go through this. So the conditional probability usually is identified by the phrase given that. So like find the probability that a randomly selected person is married given that that person has a college degree. So as long as a person has a college degree, that's what we're looking at. We're looking at all the people that have a college degree, how many people of those people are married. Sometimes it's written a little differently and it's a little more subtle, which then you got to kind of ask yourself, what are they asking? That would look like find the probability that a randomly selected person with a college degree is married. So now they're telling us they're still going to randomly select a person. We have it in our sentence. We're randomly selecting a person, but we're only randomly selecting from people with a college degree. So they're still, the sentences are asking the same thing. We're looking at the people with college degree. We're trying to find the people that are married. Does that make sense? Can everybody kind of see how that works out? I hope you do, because it is, conditional probabilities can be a little confusing, but they're fairly straightforward once you understand what's being asked when you're looking at your data. So again, the second statement implies that we're selecting from people with a college degree. So here we get a couple things we want you to identify. Are they conditional probabilities, yes or no? And then see if you can kind of figure out what they're actually asking as well. All right, so in the first one, the probability that a randomly selected teenager from the United States will go online at some point during the month is 93%. Probably a little low percentage-wise, but yes, what we're looking at. This is a conditional probability. I think I got it right. Yep, we got it right. So this is yes. It's conditional because it's a randomly selected teenager. We're just looking at the teenagers in the United States, not everybody. And then we're trying to figure out are they going to go online or not. The second one, the probability that a randomly selected adult, again, randomly selected adult, we've kind of identified who we're picking rather than data from the whole United States. So again, this one is conditional. This is yes as well. The last one is the probability that a randomly selected resident of the United States, and now we're talking about everybody in the United States, that is a teenager. So we're looking at everybody, but we want a teenager that's going to go online. Is about 7%. So here we're talking about everybody. This is one of those and statements we talked about yesterday. This is an and. Pick a person who is a teenager and will go online. Does it make sense? Does everybody kind of see that? Okay. Like before, we can use symbols to notate what we're looking for, so we kind of start working through problems. So you see the symbol, the kind of the given, the bar is what we're looking at for a conditional. So what we're looking at is the person is married, given that that person has a college degree. That's how you read the vertical bar, it's given that. So in just symbols, we can kind of go the probability of A given that B happened. So we're trying to find the probability of A knowing that B has already happened. Try to think of an example off the top of my head here. What's the probability that it's going to snow given that the temperature is 34 degrees? All right, we're just trying to figure out what's the probability it's going to snow. Typically, it doesn't snow when the weather's over 34 degrees, but sometimes it does. So there is meteorological probabilities that it could happen. That would be the conditional probability, rather than what's the probability on a given day that it's snowing and it is 34 degrees. So if you're given a table of data, it's easy to determine the conditional probability. You just kind of look at the lines. There is a formula to do if you don't have data that way in a table, where you actually have the probabilities of different events. We'll kind of look at both. The formula is the probability of both A and B happening divided by the probability of B happening. So you'll see in our example in a minute what we kind of mean by that. I'll kind of work through how that works out. Here's our example. So we're looking at the census data again. We're trying to find the probability that a person with less than a high school degree is married. So if I call is married is going to be my A value in our probability statement. This is the given. We're just looking at people with less than a college degree, a high school degree. So if we kind of look at what we're looking at in our data table, we're just looking at these people in this row. Okay? So what we're looking at is the probability that a person with less than a high school degree is married. So if we remember, our probability formula is the probability of A and B divided by the probability of B overall. Okay? So we kind of look at it, the probability of somebody being married with less than a high school degree is 70 over 125. Does that make sense? Okay. And then the probability of the person having less than a high school diploma is 125 over 665. I'm sorry, the top number is wrong. My mistake. I put the wrong values in. I put the actual answer in rather than what the value should be. My mistake. Sorry about that. So probability of A and B. What we're looking at there is the probability of somebody with less than a high school diploma out of the whole group of people. So if we look at B, the probability of B, like I had at the bottom, is 125 over 665. And then we have the probability of people being married is this number. It's the 408. So that's going to be 125 plus 408. At the top. So that would be what, 533? 533 over 125. But rather than using the formula, if we use the table, what we're looking for is the 70 married people out of 125 total people. So the actual, what we're looking at is 70 over 125. I have my formula messed up a little bit. I apologize for that. Trying to figure out why I kind of messed that up a little bit. Not quite sure. Sorry about that. So just know that when you have a table, you just want that. We'll work on one where it's a little bit more or less confusing, I guess. Sorry about that. Two common mistakes that we have when we're working with the conditional probabilities. The first is thinking that the probability of A given B is the same of probability of B given A. It doesn't work that way, because when you're looking, if we kind of go back to our table for a minute, we're looking at different values on the bottom of your fraction. If we're looking for, like our example here, the probability of somebody being married with less than a high school diploma is 70 over 125. If we flip it around and do the probability of somebody who is married having less than a college diploma, we kind of flip it, then we're looking at 408 over 100 over 70, which are two completely different probabilities. Hope that makes sense. The other one is it's not 1 over. It's not a fraction. You can't divide by that. So you have to kind of look at both of the events individually and figure out what's the probability of A given B, what's the probability of B given A. They're going to be two different numbers. You can't look at the probability of B given A as 1 divided by the probability of A given B, because again, that just doesn't work. So what we talk about is independent and dependent events for this type of conditional probability. Probability on dependent events is a little bit outside the scope of what we're doing in the class. I'll touch on it a little bit, but it does get really, really scary with the numbers we start working with. If we're looking at our values with what we've been working on, where the probabilities are different, that we can say being that education level is associated with marital status. So there's not independent event. They're not independent because the probabilities will change depending on education level and marital status. So they do change, so they're not dependent. If the probabilities aren't the same, they're going to be dependent events. Whereas independent events, no matter what happens, the probability is always going to be the same. So think of it as the probability of A given B is always going to be the probability of A. The probability that I flip a coin and get a heads, given that I've already flipped a coin and gotten a heads, is still 50%, because the probability of flipping a coin is 50-50. It's not going to matter that I've already gotten a head. It can if it's a dependent event situation, which we'll talk about in a minute. So if we kind of look at our married person as independent from a person who has a college degree, if they were independent, then the probability is going to be the same. And if we look at it, the event a person is married is independent from a person having a college degree. The probability of a person having a college degree is 143 over 165, 665. The probability of somebody being married is 408 over 665. So you can see right there, the probabilities are different. If they were the same, the probability of having a college degree with a married person would be similar to what 408 over 665 is, works out as a percentage. But because our fractions are different, our probabilities are going to be different. So there are associated events, they're not independent. So think of it this way, we're going to shuffle a deck. We're trying to decide if, first of all, take a minute and decide, is shuffling a deck and getting a card being a diamond independent of being the card being red? Logically, it doesn't make sense. So when we kind of look at it, that the probability of a 52 deck of playing cards with one dealt face down, we're trying to find out if the probability of getting a card, a diamond, is independent of the card being red. So when we think about it, if they're the same, if they're independent, the probabilities would be the same. And when we think about a deck of playing cards, remember there are 52 cards in a deck, and there are 13 diamonds. So dealing one card, the probability of A, the card being a diamond, is 13 over 52, which works out to be 1 over 4. So now the probability of getting a diamond based on the card already being red, let's think that through. The probability of cards, there are 26 red cards in the deck. right? Half the deck's red, half the deck's black. The probability of getting a diamond, though, is still 13 diamonds. So now our probability here isn't 1/4, it's 1/2. So they're not independent events because the probability of getting a diamond goes down if you already know the card's red. Whereas if the probability you didn't know the card was red, there's a 1 in 4 chance you're getting a diamond. Does that make sense? Okay. Take a few seconds, see if you can figure out the following probabilities here and see how that works out. Are they independent events? All right, so hopefully you figure that out. We're able to do it, and you have a pretty good idea what the answer is. We'll kind of go through it right now. So if I want to know if they're independent, I have to figure out what's the probability of just getting an ace straight up without even knowing the cards are a diamond yet. So when you think about it, there are 4 aces in the deck, and there are 52 cards. So my probability is 4/52, which I can simplify down to 1 out of 13, right? So that's the probability of getting an ace, straight up getting an ace. Now we're trying to find out, is that independent of getting an ace knowing that you already have a diamond? Well, let's think this through. How many diamonds are in the deck? Well, I know there are 13 diamond cards in the deck. And then from that, I know there's only 1 ace in the diamonds, the diamond suit. Just think of it, that's what cards are. So our probabilities are actually still the same. So in this instance, the probability of getting an ace is completely independent from the card being a diamond, because the probability chances are just the same. Okay. So a sequence of independent events and associated events also matter. The challenge in probability is finding a probability of a sequence event. Something happened first, what's going to happen next? So think of it this way. Consider a married couple. They plan to have 2 children. What is the probability that the first baby is going to be a boy and the second baby is going to be a girl? What do we think the chances are? Well, the chances of it being a boy are 50-50 for the first one, really, because there's only 1 or 2 options. But then now we need to know what's the probability of being a boy, the second child, knowing that we already have a boy. So that's a little trickier, because for the second child, it's still a 50-50 proposition. But we have to take into the fact that we've already had a boy, so that the probability not knowing ahead of time is a little trickier. So if we walk through our example, what actually happened is in the United States right now, the probability of babies being born a boy are 51%, a little more than half. So when we kind of look at it, our generalized formula, we're going to use what they call the multiplication rule. And the multiplication rule shows that the probability of a sequence of events is the probability of the first event times the probability of the second event, independent of what's already happened. So when we look at the probability of the first child being a boy, the probability of that is 0.51, or 51%. So that's the probability our first kid's going to be a boy. The probability of our second child being a girl now is 100 minus 51%, or 0.49. So the sequence of events, a boy, then a girl, is the probability of a boy times the probability of a girl. And I think if I remember correctly, this worked out to be 0.4 something 69, I think, when you multiply that out. So there's slightly less than a 25% chance that you're going to have a boy and then a girl. Make sense? Because the other thing too is you can kind of think of it flipping a coin. What's the probability of getting 2 heads in a row when we flip 1 coin? Well, the probability of getting a head the first time is 1/2, times the probability of getting a head the second time is 1/2, so that's going to be 1/4. The probability of getting another head now is going to be 1/4, 1/2 times 1/2 times 1/2, or 1/8. If you think back to the day when I did my random sample in class and I ended up having 10 heads in a row, well, that ends up being 1/2 to the 10th power, because we're multiplying it together 10 times, which is an astronomical number. It ends up being like a 0.00097% chance of getting 10 heads in a row flipping a coin. So here's our other example. What's the probability of flipping a coin 4 times and getting 4 straight heads? I just kind of talked you through it. Take a minute, figure out the answer, enter it in Edpuzzle. All right, so what we're looking for is always kind of draw out what your outcomes are that you're looking for. We're looking for a head, and a head, independent event, because coins don't have memory. So I have 1/2 times 1/2 times 1/2 times 1/2. So there's a 1 in 16 shot that I'm going to get 4 heads in a row. So if somebody ever bet you $1 million that they can do that, don't take the bet because they probably have a weighted coin. They're not going to bet $1 million on that. Okay. Does that make sense? Sequence of events is just multiplying stuff together. This is what we're going to work on probably next week as we start doing a lot more examples and stuff, trying to figure out the sequence of events, because that's kind of what we're looking for in some of the probabilities that I want to work with. And these get complicated because you start getting into what we're talking about is independent events. So we do something and then we go back to what we originally were, whereas dependent events start to get into the probabilities change, because think of it this way. If, in our blackjack example, if I'm playing blackjack and the first card I get dealt is an ace of clubs, the chance of my next card being a 10 kind of went down because one card's already out of the deck. So now rather than over 52 cards, I'm trying to figure out the probability of over 51 cards. So the probabilities get different. So when you start kind of thinking that, that's when it gets to be a little hairy when you're trying to figure out the probabilities. So kind of look at that. We'll work on some problems. I think tomorrow I'm going to try to put together some another one of those pair deck things where you're going through trying to figure out the probabilities, trying to figure out what probabilities of different things are to lead into our discussion and our lesson on the probabilities of blackjack and what the different things are and what are the probabilities of things happen, because those do get a little more complicated. And I'll do that lesson before we kind of get into that. So do that. Have a good day, and I will talk to everybody tomorrow.